Hey, hello guys. Good evening. Good evening to everyone. So I hope the lecture has started. Okay. Okay, so guys, welcome back. So in this lecture, we will cover units and measurements. Okay. And this is going to be mainly a backlog type of lecture. So for all the students who have a backlog in in this topic and want to quickly cover this topic, you can watch this lecture. Okay. So we will be covering the basics of this chapter itself. Everything except vernier and screw gauge, we will cover it today. Okay. And the lecture will be slightly quick, right? Because we have to finish a lot of topics under like 2-3 hours, right? So we'll be a little bit fast, but we will try to cover everything in detail. And yeah, so the duration it will be around 2.5 hours. Okay, around 2.5 hours. So by that time we'll try to finish it. Okay, so yeah, so when we start this chapter, we first talk about physical quantities, right? Because in physics, all we do is study different properties of physical quantities itself. So physical quantity, first let's understand this. So it's just any quantity out there or any property of a matter that we can measure. Okay, any property of property of matter which we can measure. Okay, so an example for this could be, imagine there is a box. Okay, a cubical box. So this box will have some mass to it, right? It will have some mass to it, and this mass you can measure it, right, using a weighing scale. Similarly, you can measure the volume of the cube. Okay, how do you measure the volume of the cube? You can measure the side length of the cube using some length measuring device and do a cube. That will give you the volume. So this volume is another quantity or property of this box which we can measure. The next thing that we can measure is the temperature of the box, right? I'm just taking a few examples. You can measure the temperature of this box as well, temperature of the air inside the box. Okay, so these kinds of properties of matter which we can measure, okay, using some process, that comes under physical quantities. Okay, and physical quantities is what we study in physics, basically in 11th and 12th, right? All the things you can name that you have seen in physics, all the equations, F equal to ma, take E equal to half mv square. These are all different physical quantities. Here we have kinetic energy, mass is another physical quantity, velocity, speed is another physical quantity. So in all these formulas, whatever you are seeing is just another physical quantity itself. Okay, so that's the first thing. And the next thing is, any physical quantity that we are going to study, it can be expressed as a number and a unit. Okay, so here itself, if I take the example of mass, how do we express mass? What are some popular units? So you guys may know kilogram. So 2 kilograms, let's say, is the mass of that box. This you can also express in grams, right? So I'm assuming you guys know how to convert kilograms to grams. 1 kg is actually 1000 grams, right? So this you can also express as 2000 grams. So basically the point is, any physical quantity, here we are talking about the mass, we can express it as a number along with a unit. Okay, so here the unit is 1 kg and the number part is 2. Here the number part is 2000 and the unit is 1 gram, right? So a few examples written over here. Mass is measured as 2 kg. A length measurement can look like this, and a time measurement can look like this, right? So in all these, we have a number as along with a unit. Okay, so that is all about physical quantity. Now the next thing is, So this you have briefly seen in 9th standard, the difference between scalars and vectors. But there is another difference. So all the physical quantities, if you take it, you can break it down into two different types, scalars and vectors. Okay, so all the physical quantities which we will study in class 11th and 12th, you can break it down into two categories, vectors and scalars. Okay, vector quantities and scalar quantities. Okay, roughly you can break it down into vectors and scalars, and the main difference between vectors and scalars has to do with direction, right? So scalar quantities, basically the examples for them are mass, distance, time. These are some examples that you know, right? So these are quantities which have only magnitude and we don't need any direction to express them. Okay, so they don't have any direction associated with it. Or a better definition for scalars is, if you simply have the magnitude of the scalar, by magnitude I mean if you're taking the mass 12 kg, okay, this is the magnitude of the mass. If you simply have the magnitude of a scalar, then you can fully study it, okay, or you can fully understand the quantity. So if somebody tells you that the distance they covered is 1 kilometer, there is no additional information needed in that description. So scalars are those quantities for which we only need a number or the magnitude part. We don't need any direction information. Let's say the time elapsed is 15 hours. Like we don't need to know any directional information in that. So those kind of quantities come under scalars, which we can completely describe using the magnitude alone. Okay. So these are some examples: energy, work, temperature, speed, power, volume, pressure. So, and there are more scalars and vectors which we will see as 11th and 12th progresses. So then we have vector quantities. Some popular vectors you already know from 9th standard: displacement, velocity, acceleration, force. What is special about these? The speciality about these is they not only have a magnitude. So force is a nice example to understand that. So if I have a block of mass that is placed on the ground, okay, if this block of mass is placed on the ground, then we can exert a force on this block. Let's say we are applying a force at this point, right? And we can apply the force in any direction. Let's say this arrow is there to tell us about the direction of the force. We can apply it horizontally, we can apply it vertically, we can apply it in this direction. So it's not only important how big the force is, which is how much is the magnitude of the force. So force, let's take it as 50 Newton. Okay, force SI unit, you guys should be remembering it is newtons, right? So it's not only the magnitude that is important, also the direction, okay, which you can think as this angle theta. So you can apply this force in any angle, right? And in all those angles, the force will be different. So in force, we not only need the magnitude, but also the direction. Hence, this is classified as a vector, right? This we classify as a vector quantity. Similarly, electric field, magnetic field, these are quantities we will see in class 12th. Momentum also we will see in 11th itself. Displacement, velocity, acceleration, also same logic. The velocity of an object. For the velocity of an object, if we have some object which is traveling at a speed of 20 meters per second, it's not only enough to know the speed, right, but also the direction in which it is moving. So in this case, I'm saying it is moving to the east. So in velocity, when we are talking about the velocity of an object, we also need to specify the direction. So not only the magnitude, but also the direction. 20 meters per second east. Same is the story with displacement. Displacement and velocity we'll study in detail in the upcoming lectures. Okay, so vectors, they are represented by, they have both magnitude and direction, and we need both magnitude and direction to completely study them. Okay, These factors we will study in the next chapter. Okay, we'll have vectors in the upcoming lecture. All right. So then we have something. So we discussed the physical quantities, how they are distributed as vectors and scalars depending upon do they need extra information regarding the direction or not, right? There is also another important classification, which is of all the physical quantities, okay, 7 of them, there are 7 physical quantities which are called as the fundamental quantities, and these are chosen as the fundamental quantities by convention. Okay, this is the rule. Okay, there are these 7 fundamental quantities, and these fundamental quantities are chosen as convention. Okay, and everybody else, every other physical quantity is derived, is known as derived physical quantity. Any physical quantity is which is not under this 7 is known as a derived quantity. Okay, so I'll explain what is the difference. So fundamental quantities, which are the fundamental quantities, they are also important. Okay, so length is one of the fundamental quantities, mass, time, these three will be the most important for us as of now. Then we have temperature, electric current, amount of substance, okay, and luminous intensity. So these 7 quantities come under the fundamental physical quantities. Okay, and there, this is the SI unit. So this is actually the SI unit for these quantities. Okay, and length, most of you already know, the SI unit is meter, mass is measured in kilograms, time in seconds, temperature's SI unit is Kelvin. Okay, electric current from 10th standard, you must remember, it is measured in amperes. Amount of substance, so this is a chemistry idea mostly. Amount of substance is measured in moles, right? And then we have luminous intensity. So this is a light phenomena. You can think of this like the more the luminous intensity of a bulb, let's say. Okay, so imagine that we have a bulb that is lighting up a room. Okay, more the luminous intensity of this bulb, the brighter the room gets. Okay, and its SI unit is candela. Okay, it's similar to candles. So so yeah, these are the 7 fundamental quantities, and anybody who's not on this list comes under the group of the derived quantities. Okay, so so only these guys have a unit that is specifically defined. Like for length, it is meter, and time, it is seconds, right? But velocity, if you notice, it is not in this group, right? Velocity or speed, let's take speed, is not in this group, right? So what is the unit of speed? It has to be derived. Speed is not fundamental, so it does not have a unit by itself. We have to derive the unit of speed using this list. So we know speed is the ratio of a distance over time, right? It's a ratio of a distance over time. So distance is basically a length measurement, and length's SI unit is meters, and in the denominator we have time, time's SI unit is second. So this unit that we derived, meters per second or meter by second, this is the unit of speed. Okay, so like how I derive the unit for speed, you can derive the unit for any other physical quantity which is not in this list. Okay, so that is it. So the fundamental quantities are basically you can say independent. Okay, and the other quantities, their units will be derived. Okay, their units will be derived. Now these are some derived quantity examples. Okay, area is another derived quantity, right? So it's a length measurement into a length measurement. Okay, you can take any formula you learnt in class 11th. it will have two length multiplications, right? So area of a circle, it was pi r square. So here it is r into r. Area of a rectangle was a into b. Two length measurements, two length multiplications. What else? Area of a square is a square. Area of a triangle is half bh. In all these, it is a length multiplied by another length, right? So when we have a length into length, SI unit of length is meters. SI unit of length is also meters. So the unit of area will be meter into meter, which is meter square. Same logic apply to volume. It's a length cube. In all formulas we have length cubed. So the SI unit will be meter cube. Velocity we already discussed is the same logic as speed. So its unit will be meters per second. And acceleration, we will see the definitions later, but it's a velocity divided by time type of a formula for acceleration, right? Acceleration is, you can remember it as velocity by time for now. We will study it in depth later. So velocity was meter per second, but there is also another second in the denominator. So it will become meter per second square. Okay. So that's the SI unit of acceleration. Then, yeah, so basically this is like a difference between these two, which, you know, in case you want to study it for boards, you can study it. You can take a look at this. But yeah, you will get the notes after the lecture, guys. It will be in the description itself. So the fundamental quantities are basically independent of everybody. They have their own units, okay? And there are exactly 7 SI based quantities and they have their own units, right? And the 7 units we already took a look at. The derived quantities, there are unlimited of them and they depend on one or more fundamental quantities, okay? Like for example, velocity, it was dependent on length and time, right? Which are two fundamental quantities. So the derived quantities, they will depend on some fundamental quantities, okay? And their units are derived and the examples are velocity, force, energy, basically anything that is not in that 7 quantity list, okay? So now we'll get into dimensions. So dimensional analysis and dimensions are very important for NEET, okay? In fact, most of the PYQs are either from dimensions or from the errors part, okay? So dimensions is basically for any derived quantity, right? Like velocity. Velocity we just studied, it is dependent on length and time. These are the fundamental quantities in which velocity depends. So dimensions also help us understand for any physical quantity, what are the fundamental quantities it depends on, okay? So velocity, we know it is, it can be written as a length divided by time. So its dimensions we will represent it like this, a square bracket, inside we will put velocity. It is going to be length to the power 1 because length is in the numerator and time is in the denominator, right? So that we will write it as t to the power minus 1. So what the dimension helps us understand is that this quantity velocity, it depends on length and time, as length and time are the fundamental quantities in which the velocity depends on, okay? Dimensions indicate how a physical quantity depends on the fundamental quantities. So we'll learn how to find the dimensions of different quantities now. And yeah, so before that, what are the dimensional formula for the fundamental quantities? So length we will represent using the symbol L, okay? Mass we will use the symbol M. For time we will use capital T. For electric current, we won't really need it right now, but in class 12th we will see current being used at different locations, especially in the magnetic field. If you want to find the magnetic field dimension, you will need current and stuff, right? Then temperatures temperature will be represented as Kelvin. The symbol is K. Okay. Amount of substance will be like in dimensional brackets, you will represent it as mole, MOL. And luminous intensity we will rarely see, but in case it is needed, it is represented as CD, candela. Okay. Then, yeah, so now we will write down the dimensional formulas. So area, we saw that it was a length into length, right? So length square. So dimension of area, if you want, it is easy. It is going to be L square. And just put it in a bracket. This is the dimension of area. What about volume? Volume's dimension. Volume is a length cube type of a measurement. So this guy's dimension is L cube. Okay. Length, you will write it as L. Mass density. So mass density, if we call it using the symbol rho, it is mass by volume. We know the dimension of mass and volume, so we can write the dimension of density. It will be the dimension of mass divided by the dimension of volume. So dimension of mass is m itself. Dimension of volume is L cube. L cube going to the numerator will make it L raised to minus 3. So this is the dimension of mass density. Frequency, if you remember the formula, there was a formula for frequency which is 1 by time period, okay, which we'll cover in SHM. So frequency has dimensions of 1 by time. So dimension of frequency is t to the power negative 1. Time is in the denominator, so it will be t to the power negative 1. Velocity, speed, we already saw. This guy's dimension will be Lt raised to minus 1. Okay, so these are some dimensional formulas. What about acceleration? It will be Lt raised to minus 2 meters per second square, right? And force, always think of a formula relating the quantity that you want. So if you want force, think of it using Newton's second law, F equal to ma. So here force is related to mass and acceleration. So there is something known as law dimensional homogeneity, which means if you have any physics equation, which we cover in 11th and 12th, any physics equation you can take, the dimensions of the left side is the same as the dimensions of the right side. Okay, it has to be true always. So if you want the dimension of force, it will be dimension of mass, which is m, into dimension of acceleration, which is Lt minus 2. So this is the dimension of force. Okay. Similarly for, so this quantity work we will cover later. Okay. Just for now, remember that work and energy have the same dimension. And energy, you can use any formula where energy exists. So you can use the kinetic energy formula, which was half mv square. Okay. So dimension of energy will be, so half is just a constant, dimensionless, so throw it away. So what is left is dimension of mass, which is m. Now here we have speed square, right? So speed's dimension is Lt minus 1, if you remember. This was the dimension of speed, and then we have to square it. So what will this become? L square t raised to minus 2. So just put it here, m L square t raised to minus 2. This is the dimension of energy. Okay, that is the dimension of energy. And power. So power, for now, just remember it as rate of doing work. Okay, we'll see the exact definitions in work, power, energy. But power, just remember it as work by time for now. Work by time for now. And work has the same unit as energy, right? So power's dimension will be Energy's dimension, which is ml square t raised to minus 2, written over here, divided by time. Okay, take the time to the numerator. So this will be ml square t raised to minus 3. This will be the dimension of power. Okay. All right. Now, so now the thing is, there are some more. Okay, so there are actually 3 more. So momentum, we use the symbol P to represent it. It is simply mass into velocity. But right now, we just need the formula. So dimension of momentum will be dimension of mass into velocity, which is LT minus 1. Okay. Then, okay, so angle is actually a dimensionless quantity. Okay, the angle is a dimensionless quantity. So dimensionless quantities, we can write it like this: m raised to 0, l raised to 0, t raised to 0. Okay. Angle has no dimension because it is defined that way. Okay. Like if you take a circle and if you mark down an arc of a circle like this, the length of this arc, if you write it as, let's say, S, and the radius of the circle is R, then this angle theta, it is defined as the arc length divided by the radius. So here the arc length is S, radius is also R, and here if you notice, it's a length by length, right? It's a length divided by another length. If you take a look at the angle theta, that's why it is a dimensionless quantity. So this will be the angle theta will be a dimensionless quantity. Okay. So then charge, how do we get the dimension of charge? So think of a formula in which we had charge from class 10th. So if you remember the definition of current, it was the rate of flow of charge, right? Charge by time. Right, so we remember a formula relating current to charge and time. So so now what we can do is we can use this relation to find a dimension of charge. Okay, so what will be the dimension of charge? I'm using the symbol Q for charge. Okay, it will be dimension of current. Now current is a fundamental quantity, and we noted that there. We represent it as A, right? In the dimension box, we represent it as A. So A raised to 1 multiplied with time, right? So into T. A into T will be the dimension of charge. Okay. So okay. So these are some standard physical quantities which you should be knowing. There are, of course, a lot of physical quantities which we'll cover, in 11th and 12th combined, but we don't have to study them all here because we will study them one by one anyway with time. But there's we can also just do the dimensional formula for G. This is very important. The universal gravitational constant. Okay, this is consistently asked in the NEET exam, so it's worth deriving the dimensions of G. So where did we see G? We saw G in the Newton's law of gravitation, right? So Newton's law of gravitation was supposed to give us, it gives us the force of attraction between two masses, right? When we have two masses m1 and m2, these masses attract each other with a force F, and this force was given to us by Newton's law of gravitation. Its magnitude g m1 m2 divided by distance between them square. So from this formula we can pick out the g separately. So g, if you solve for it, it is F into r square divided by m1 m2. F into r square divided by m1 m2. Now we have derived the dimension of all these stuff, right? So now we can easily derive the dimension of g. Dimension of force was mass into acceleration, mlt minus 2. Dimension of r square, r is a distance, right? So it will be length square. M1 and m2 are masses, so we can write it as m square. So this becomes m, in the numerator we have power 1, denominator 2. So overall power will be 1 minus 2, which is minus 1. L square into L will make it an L cube. And t's power is t raised to minus 2. M raised to minus 1, L cube, t raised to minus 2. This is the dimensional formula of universal gravitational constant G. Okay. So this is, you can remember it also if you want. Okay, this is quite important. All right. Okay. Now, so now we will use the dimensional formula to do some stuff. First is we will learn how to convert units. Okay, how to jump from one unit system to another unit system. So the thing is, there are some other unit system other than SI. So SI we are familiar with. The CGS is, I mean, it's not that complicated. C stands for centimeter. Okay. G stands for grams. And S stands for seconds. Okay. That is what it means. So this is a system which earlier on only had length, mass and time as its quantities, okay, and its units were centimeter, grams and second. So in short form it is CGS. And what about MKS? MKS is meter, kilogram, second, okay, meter, kilogram, second. And FPS is foot, pound, second. This we won't need that much. Foot, pound, second. Okay, and there are other unit systems as well. But in all these systems, different units for different quantities are chosen. Okay, so length in parts of the world where FPS system is used, length is measured in foot, right? Length over there is commonly mentioned in feet, foot and inches. So now, so how do we convert a physical quantity from one unit to another unit? So the thing you need to understand is the primary concept is the magnitude of a physical quantity remains the same irrespective of which system of units you use. Like a simple example for this is, if you are having a length of an object whose length is 1 meter with you, it doesn't matter if you represent it in the meter system. You can also represent it as centimeters. You can represent it as 100 centimeters as well, or 1000 millimeters. It doesn't matter. It's the same length. Okay, the length of the rod L will be the same irrespective of which unit system you use. So the main concept is the magnitude of a physical quantity, it remains the same. So if the length of the rod is L, it will always be L. There is no difference. So you can say that whichever unit system you choose, the numerical value into unit, this is the magnitude, right? Numerical value into unit is the magnitude of the length, or basically anything. this will remain a constant. Okay, so we can make a relation something like this: numerical value in the first unit system into unit of the first system is equal to N2 U2. Numerical value in the second system into unit of the second system. So you can draw that, you can compare that with this. Okay, here N1 is 1, U1 is meter. Here N2 is 100, U2 is centimeter. Okay, so 1 meter is basically the same as 100 centimeter. There is no difference. So this is the main formula we will be using to convert. Okay, to convert from one unit to another unit. So now the thing is, okay, this actually I'll take the help of an example to explain this. But in units, the units of a quantity, this we can also determine using the dimensions, right? So what was the dimension of the velocity or speed? It was LT minus 1, right? So you can also derive the units using this. The unit, so L is, let's say we are talking about the SI unit. In SI unit, length unit is meter and time unit is second. So what is the unit? Meters per second, right? So in the CGS unit system, the unit will be length is measured in centimeters, time is measured in seconds, so centimeter per second. So using the dimension, you can figure out the unit as well. Okay, so this I'll explain using an example, then it will be clear. Yeah, so the key points are the physical quantity, whatever it is, it can be a rod's length or mass or whatever. This does not change if you change from a unit system. If you write it as 1 kilogram or 1000 grams, it's the same. Okay, there is no difference. That's the first thing. Only its numerical value and unit changes. Okay, so here kilogram is a very big unit, so that's why the numerical value is small. Here gram is a very tiny unit, that's why 1000, right? Numerical value is 1000. So a larger unit corresponds to a smaller numerical value. If you take a big unit, you need a small numerical value. Okay, so so this we already covered. In the CGS system, these are the units of the quantities. Okay, MK system, these are the ones, and SI system, these are the units. This also we covered. So now let's do this example. We have to convert 1 Newton. So Newton is the SI unit of force. Okay, the SI unit of force. So 1 Newton, we have to convert it into dynes. Okay, I don't know the exact numerical value. Let's call it X. So we need to convert it into this unit known as dynes. Dyne. Okay. Dyne. Using dimensional analysis. Okay, and yeah. So dyne they have not mentioned. Yeah. So this is the CGS unit. Dyne is the CGS unit of force. Okay, CGS system unit of force. Newton is the SI unit, dyne is the CGS unit. So we will use the relation N1 U1 is equal to N2 U2. Okay, now to get the unit, we will use the dimensions. Okay, what is the dimension of force? Dimension is the same everywhere. It will be MLT raised to minus 2. This is the dimension of force. So if let's say the first unit system is the SI unit system. So N1 is 1, U1 is 1 Newton, right? So 1 Newton I will write it using this. Mass to the power 1. So that is kg length to the power 1. So I will actually write it like this. So N1 is 1. Mass unit is 1 kg. Length unit is 1 meter. Okay. Then divided by time square. Times unit is 1 second squared. This is what we call 1 Newton, kg meter per second square. Okay. Now, N2 we don't know, that is this x, right? So we can write it as x itself. Now, for the second unit system, this is the CGS unit system. This is the CGS. So in CGS, what is mass? Grams, in grams, right? So 1 gram. Length is measured in 1 centimeter. Length unit is 1 centimeter divided by time square. Time is still measured in 1 second. Seconds. So there is no difference there. Okay. So in CGS unit, what is the unit of force? It is 1 gram into 1 second divided by 1 second square. Now what we can do is we can use what we already know. I want to cancel this gram, but here we have a kilogram, right? So I'll write this 1 kg as 1000 grams. This 1 meter, I will write it as 100 centimeter. Second, I don't have to do anything because it will get cancelled. On the right hand side, I don't have to do anything. It is 1 gram into 1 centimeter divided by 1 second square. Now just cancel out all the unit part. Gram, centimeter, second square. Cancel it. Then you will get x. So x will be 1000 into 100, which I can write it as 10 raised to 5. Okay. So we finally got x. So if we have x, we can get a conversion. 1 Newton is equal to 10 raised to 5 dyne. So if you want to convert Newton to dyne, all you have to do is use this conversion formula. Okay. So this is what we were trying to find, and we use dimensions and the N1 U1 is equal to N2 U2 formula, right? Now there is also another unit for energy. This you guys try out as homework. So energy's unit is 1 joule, right? This you have to convert it into this new unit called erg. So erg is the CGS unit of energy, and joule is the SI unit of energy. Just use the process we used to find the conversion for Newton and you will get the answer. Okay. So try this out as homework. Okay, so this question is we have to convert 2 joules into a system of units. Okay, so here they are not telling us it's a CGS unit or something. They are saying it's a new unit system. And the unit of mass in that system is 10 gram. Unit of length is 20 meters. And unit of time is 10 seconds. This is the unit. Okay. So let's do the conversion. So first of all, we are talking about joules, right? So we are talking about energy here. What was energy's dimension? Energy's dimension was ml square t raised to minus 2. Mass into velocity square, right? So if I want to write the SI unit, U1, mass is measured in kg, length is measured in meters, time is measured in seconds. Okay. So this is U1. What about U2? In the second unit system, mass is measured, mass unit is 10 gram, okay, and length unit is 20 meters, but you have to square it, like, right, length unit you have to square, and time unit is 10 seconds raised to minus 2. So what does this come out to be? 10 into 400, 20 square is 400. And here we have 1 by 10 square, which is 1 by 100. So this comes out to be 40, right? So this turns out to be 40 gram meter square per second square. Gram meter square per second square. This is the unit in the second system. Unit of the energy in second system. Okay. Now apply N1 U1 equals N2 U2. So N1 was 2 joules, right? So 2 is the numerical value. Unit is kg meter square per second square. So instead of kg, I am converting it into grams. So kg, I am writing it as 1000 grams. Gram meter square per second square. This is U1. Numerical value 2 is what we want. So that I am going to write it as N2. U2 is 40 gram meter square per second square. So now cancel the unit part. So N2 comes out to be 200 divided by 4, which is 50. N2 comes out to be 50. So in the new unit system, the numerical part is 50. Okay. So that is it. This 50 is the answer. So unit conversion problems, first find the units, okay, and then apply N1 U1 equal to N2 U2. For finding units, use dimensional analysis. That's all you have to do. All right. Now, so that was the first use of dimensions. We can convert between units. Okay. The second use is we can check if equations are correct or not. Okay. And we can also find dimensions of unknown quantities. So there is something known as the principle of homogeneity, okay, of dimensions. The idea is simple. Any physics formula you know, just pick it up. Take S is equal to ut plus half at square, or F equal to ma. Kinetic energy is equal to half mv square. Any formula you guys know. V equal to IR. Just throw all the equations you know. Dimensional homogeneity says what it says is the left hand side and the right hand side must have the same dimension. Otherwise, it cannot be a correct equation. Okay. So V has the same dimension as IR. Here the logic is slightly different. S has the same dimension as UT, and UT has the same dimension as half AT square. Okay, UT has the same dimension as half AT square. These terms must have the same dimension on the left hand side and the right hand side. If this is satisfied, then the equation is called dimensionally homogeneous, which means it has the same dimension on both sides, or dimensionally correct. Okay. If there is an equation which does not follow this, like let's say you mess with one of these equations, let's say you wrote F as ma square. Here the dimensions won't match. Okay, so this equation will be dimensionally Wrong. Okay. So that is principle of homogeneity. Basically, left side and right side must have the same dimension. Okay. Not just that, if you are, let's say, adding two quantities to get a third quantity, okay, this A, B and C can be any quantity. Okay. Here, if you are adding A and B, what are we doing? We are adding quantity A and B, right? Now, we cannot add a mass measurement to a length measurement, right? So, like for example, let's say the dimension of A is mass, okay, m raised to 1, and dimension of B is L, which is the length. Adding a mass measurement like 5 kg to a length measurement like 10 meters does not make sense, right? If you add 5 kg to 10 meters, this is meaningless, right? You're adding random stuff. So if you are adding two quantities, okay, this is an important thing from exam POV as well, point of view. If you see any two quantities being added, then they must have the same direction, right? Sorry, not direction, dimension. They must have the same dimension. Otherwise, you can't add them. Okay. So here we are adding A and B. So which means dimension of A, whatever that may be, it has to be the same as the dimension of B. Now, of course, if for example, this is a mass, then you add mass to mass, then the output will also be a mass, right? So C will also have the same dimension. Okay, so if you see any equations like this, when you add two things to get a third thing, then all of them will have the same dimension. Okay, same with subtraction. Same with subtraction. Here also dimension of A is the same as dimension of B as dimension of C. Because if the dimension is not same, that means these are different quantities. Like you're adding some length type, adding some length to a mass or length to a temperature. Okay, that doesn't make sense. So that is this fact. Okay, so like in exams, like in the NEET exam, you can check out the previous year questions. They will give you an equation like this. Okay, and here the thing is, and they will ask you what is the unit of A, for example. Okay, and here instead of B, they will give you energy, not energy. Let's take it, let's take something. Let's say velocity, Vt. Okay, they'll give you something like this. Here E is energy. Let's actually solve this question. Okay, so energy is given as A into T square. T is time, and divided by Vt. V is speed, T is time, minus B. Okay, this equation is given to us, and they're asking find dimension of A and B. Find dimension of these unknown quantities A and B. So here the first thing that should click in your head is B and Vt are being subtracted in the denominator, which means dimension of B must be the same as the dimension of Vt. Okay, otherwise you cannot subtract them. Vt is actually distance. Speed into time is distance, if you remember. So this will be L. So dimension of B will be length. Okay, it's simply L power 1. Now what we'll do is we'll take the dimension on both sides. So dimension of energy, or basically just resolve for A. If you solve for A, it will be E into Vt minus B divided by T square, right? Now take the dimension on both sides. So dimension of A will be dimension of energy, which is ml square T raised to minus 2. This is dimension of energy. into dimension of this bracket. Now, how do we write the dimension of this bracket? This whole bracket is simply a length, right? Some length. This is a length minus length, so this whole thing will also be a length. So its dimension will be L divided by time square. Okay. So what will this be? Mass power is m raised to 1, L cube, t raised to minus 4, t raised to minus 4. This is the dimension of A. Okay, so these types of questions are asked in your NEET exam. So these are important. So here the first hint is if two things are being added or subtracted, their dimension is the same. Okay. Okay, so now, so we can check if an equation is dimensionally correct or not, right? Using principle of homogeneity. Find the dimension of unknown physical quantities or constants. That is what we did in this question, okay? And derive relations between physical quantities, that we will do. So check dimensional correctness, you can just use any formula, S equal to, let's say, ut plus half at square. This was the 9th standard formula. So here S was displacement, right? Displacement is basically having a unit of meters, so its dimension is L. What about ut? Ut is velocity into time. So its dimension will be Lt raised to minus 1 into t raised to 1. So this will be L itself, right? I mean, it has to be L. And half at square, half is just a constant. A is Lt raised to minus 2. T square is, time square is t square. This is also L itself. This is also L itself. So these three terms have length dimension. Of course, it has to have length dimension because you can only add a length to another length and get another length, right? You cannot add a length to a mass. So dimensions are useful in that way because we can test or check if the equation is correct or is there something wrong with the equation. So now we will derive an expression for the time period of a pendulum, okay, using dimensions. So the thing is, we don't know the, okay, so this is the exact formula for the time period, but we are trying to derive a formula which looks like this, okay. So the time period of a simple pendulum, so simple pendulum is basically, you're hanging a ball by a thread and we are leaving it from some angle theta, so it will oscillate back and forth, right? So the time it takes for one oscillation, that is what we call as a time period. So it will basically depend on two things, right? First is the length of this wire and gravity g. These are the stuff it will depend on mainly. This, of course, we need some Newton's laws to understand that. But right now I am telling you this time, it depends on the length and the value of g somehow. We don't know the exact powers, so I am taking x and y. So the time period, I don't know what it depends on, but it must depend on the length and value of g. And I also don't know the power to which it depends on. So I took the powers as x and y. Now just get rid of the constant proportionality and basically write it like this, a dimensionless constant into length raised to x and g raised to y. Now here, now do dimensional analysis on both sides. Dimension of t is t itself. K is dimensionless, so throw it away. L is length, right? So L raised to x. Then what about g? This is an acceleration. G is acceleration, right? Acceleration due to gravity. So I can write it as LT raised to minus 1, the whole raised to y. Okay, I can write it this way. Now club L together. So there is an L raised to x and an L raised to y. So this will become L raised to x plus y and T raised to minus y. T raised to minus y. Okay, T raised to minus y. So now dimension here and here should be the same. So there is no length on the left side. No length means it is length raised to 0, right? That is what no length means. Now compare the power. X plus y should be equal to 0. That's the first equation. Times power is 1. So 1 is equal to, hold on. So this will be LT raised to minus 2, right? So times power will be minus 2y, not minus y. So 1 must be equal to minus 2y. So from here we get y, the power y, as negative half. So if you put that here, you will get x as positive half, x as plus half. Now, once you have x and y, you can get an approximate formula. So time period is k into L raised to x, which is L raised to half, and g raised to y, which is minus half. So this is k into root L divided by root g, which is k square root of L by g. Yes, using dimensions, we cannot find this constant k, which is 2 pi. We cannot find that, but we can get the dependency on length and g using dimension. Okay, so that is how we use dimensions to find the approximate formula. Okay, so that is it. That is mainly it. If a question from this appears, they will say that some physical quantity Q, it depends on some quantity A and some quantity B and some quantity C. Okay, and this will be like force, velocity, energy, something like that. So if it depends on them, then you don't know the power. So you put X, Y, and Z, and then you solve it like that. Okay. And then you find X, Y, and Z, and then you will get the approximate formula. Find X, Y, Z. You will get the approx, not approx, but a formula without a constant. Okay, but you guys get the idea. So I'm just writing approx. You'll get an approx formula, right? Like here we cannot find out k using dimensions, but we got the root L by g. So we can find the dependency of A, B, and C, but we cannot find the constant. Okay, so that is it. Then yeah, we have to check if this is dimensionally correct or not. P equal to mv by 2. Now we can directly say it is correct, but to check it, yeah, so on the left side we have momentum and on the right hand side we have mv by 2. This is dimensionally correct because momentum's dimension is the same as mv's dimension, right? But this equation is wrong, as you can see. We know that momentum is actually equal to mv. So the equation is fundamentally wrong. Equation is fundamentally wrong. But dimensionally it is correct, right? Dimension wise, left and right side are correct. But if you, because of this 2, this equation becomes wrong. Okay. So that is the idea. Like in the S is equal to ut plus half at square. Like instead of that half at square, you wrote at square. This equation is wrong, but dimensions are fine, right? Dimensions are okay here, but the equation is wrong. Correct equation is with a half here. So that's the thing. So now we have another question. Here we have to find the dimension of the unknown quantities P and Q. So there is a quantity P and another quantity Q. So Q is inside cos. So there is something about trigonometric functions. Okay. So trigonometric functions, whichever function that may be, sine of something, cos of something, these are dimensionless. Okay. These are dimensionless. And the inside things are also dimensionless. So if let's say this is alpha and beta, okay, then whatever is inside sine and inside the trigonometric functions, these are also dimensionless. So because inside, so basically the input and the output are both dimensionless. For whenever you see a trigonometric function, it's also true for other functions as well, logarithmic or exponential. Then also this is true. Like it can be a log of alpha, then also this is true, or it can be an e raised to alpha, then also this is true. Okay. Basically the input and the output will be dimensionless. So here on the left side we have a potential energy, right? Potential energy means energy itself. So ml square. What is the dimension? ml square t raised to minus 2. Then we have dimension of P into dimension of this cos. Cos of whatever it may be, it is dimensionless. So which means P's dimension is ml square t raised to minus 2, which is energy's dimension. Okay. Now for Q, what we can do is whatever is inside the cos is also dimensionless. So this thing Qt is dimensionless. Qt is dimensionless. So you can write it as m raised to 0, l raised to 0, t raised to 0. Okay. Qt must be dimensionless. Dimensionless. So from here you can get dimension of Q. That will be, so send this t to the denominator. If it goes to the numerator, it will become t raised to minus 1. This is the dimension of Q. Okay. So just remember, cos, whenever you have a trigonometric function, the input is dimensionless and also the output. So this whole cos, whatever it is, that is also dimensionless. And Qt plus pi by 6, Qt plus pi by 6 is also dimensionless whenever you have a trigonometric function. Okay, so now this is the next question. So here alpha is given as f divided by v square into sine beta t. So we have to find dimension of alpha and beta. So we see a sign, right? We can notice a sign here. So this thing is dimensionless. This thing is dimensionless, and the inside thing, beta t, is also dimensionless. So this is the same as the previous one. So beta's dimension will be t raised to minus 1, right? Beta should be t raised to minus 1, so that t raised to minus 1 into t gives you dimensionless. Now we can find alpha. Alpha's dimension will be dimension of force divided by dimension of velocity or speed square, right? Okay, so from here, what is force dimension? ml, no, there won't be a square here. For force, it is ml t raised to minus 2. And for speed square, it is L square T raised to minus 2. So these common dimensions should be on your mind, guys, for speed, etc. So ml raised to minus 1, T raised to minus 2 cancels, right? So this will be the dimension. This will be the dimension of alpha. Okay. So that is how we do it when we have a trigonometry function in the expression. Okay. So now we are going to take a look at significant figures. Okay. And rounding off basically. So significant figures are the digits in a measured quantity that are known with certainty along with one estimated digit, which is usually the last digit. So what this means is, let's say we measured the mass of an object, okay, and that mass of the object by the instrument, it came out to be 12.038 grams. Okay, this is what we got for the mass. Now the thing is, we don't know what comes after this 8, right? So we are not even sure if this is going to be 8. For example, this could have been 0.037, right? And the next digit, if it was 7, 8, and somehow the device mentioned it as 8. The last digit could have been 7 also. Similarly, it could have been 9 also, 039. So we are kind of not that confident by this 8. The other digits are fine, but the 8 we are not so confident about. So this last digit is what is called as the uncertain digit. Okay. This last digit in the mass measurement is what we term as the uncertain digit. Okay. And the other are certain. Okay. The other are okay. We're confident about the other digits. So the significant figures, if you want to count of any measurement, it's simply all the digits, all the certain digits 1, 2, 0, 3 and the uncertain digit. So here we will have 5 significant digits. 5 significant digits or 5 significant figures. Okay. So basically, there are some rules to counting the significant figures, which is important for the examination. That is what we are going to be learning. Okay. And another important idea is significant figures helps us, indicate the precision of the measurement. And it's kind of a measure of how good the measurement device is. The more the number of significant figures, the better the measuring instrument. Okay, we'll get into that. But yeah, in this length measurement 12.34, number of significant figures is 1, 2, 3, 4. We have 4 significant figures. Okay, 1, 2, 3 are the certain digits. We are confident about them, but the last digit we are kind of uncertain about. Okay, hence 12.34 centimeters have 4 significant figures. Now we'll take a look at that precision thing. If you measure the length of a rod, okay, using a ruler, a normal ruler's least count is the smallest length you can measure with it, right? That is 0.1 centimeter using a normal ruler. It turned out as 12.3 centimeter, let's say. So you measured the length of the rod as 12.3 centimeter using a normal ruler. So the ruler, of course, cannot measure beyond 0.1 centimeter. So you report only 3 figures, right? Like if the ruler could measure 0.01 centimeter, then you can also measure it like 12.30 centimeter. But because it can only measure 0.1 up to 0.1, you will only get a 12.3, 12.5, 12.7, something like that. Okay, you will not get 12.34. You cannot know about the next digit. The next digit you can only find using a better device. So therefore we use vernier calipers. Vernier calipers is basically also another length measuring device, but this guy's least count is 0.01. So this guy can measure smaller lengths, right? The ruler can only measure up to 0.1 centimeters, but this guy can measure even smaller lengths up to 0.01 centimeter. So here we will have two decimal places basically. If you are writing it in centimeters, you will get two decimal places. And then you got the length as 12.34. Here you only got 12.3. So this is said to be more precise. Okay, this is said to be more precise. When you have information about more digits, this is said to be more precise. Okay, 12.34 is a more precise measurement as compared to 12.3. So now you can measure an extra decimal place, and if you notice the significant figures is now 4, right? So more the number of significant figures, more is the precision of the measuring device. Then we have screw gauge, which takes it up another notch. This guy can measure up to 0.001 centimeters. Okay. So here we will have 3 decimal places. This guy can measure up to 3 decimal places. So here we have 5 significant figures. So this will be the most precise measurement. Okay, this will be the most precise measurement. So if I have to arrange ruler, vernier caliper and screw gauge in the order of precision, of course screw gauge will be the most precise because it can tell us up to information of 3 decimal places. But here we only get to know about 1 decimal place, and here we only get to know up to 2 decimal places, right? So more number of significant figures, better the precision of the measuring device. So now so now the thing is, there are some rules that are important. These are NCERT rules itself, okay, for counting the number of significant figures. So if you're given a number, how to count the number of significant figures? So first rule is easy. Wherever you see a non-zero number in that number, like here we have 1984. These are 4 non-zero numbers. Count them as significant. Okay. So 1984 has 4 significant figures. So that is easy. Rule 1 means, rule 1 is telling us non-zero digits are significant. All the zeros between 2 non-zero digits are significant. So if you have 2 non-zero digits, let's say 1 and 5, and we have 3 zeros sandwiched between this 1 and 5, then these zeros are significant. Okay, these are significant figures. These zeros, significant zeros. So any zero that is sandwiched between 2 non-zero digits are also significant. So here these 2 zeros are significant basically. Then rule 3 is all 0 to the left of the first non-zero digit, ignore them. So first non-zero digit is this 1. So these 2 zeros are not significant. Okay, these 2 zeros are not significant. Hence it only has 1, 0 and 8 as the significant figures. Okay. If the number is less than 1, the zeros to the right of the decimal point but to the left of the first non-zero digit are not significant. Okay, number less than 1 means it should be like 0.0345, something like that. This will be a 0, and on the right side you can have anything, right? So here there is an example given, 0.002308, right? So here the thing is, 2 is the first non-zero digit. Any 0 that comes to the left of it is not significant. is going to be not significant. Okay. Basically the same as here only. There's no difference. Basically, any zero that comes before the first non-zero digit is not significant. Okay. Then trailing zeros, which means zeros that come at the end of a number containing a decimal point, are significant. So here the thing is, we have a decimal point and we have one trailing zero. One trailing zero. Trailing zero means zeros that come to the end. Okay, come at the end. So how many significant? 1, 2, 3, 4. Okay. Now, if there is no decimal point, this is important, then the trailing zeros in a number may or may not be significant. Okay. Like for example, 101.10100 has 3 significant figures, but this is kind of ambiguous. Okay. This rule is kind of ambiguous, which means this creates a confusion. Like to avoid this confusion, what we use is something known as a scientific notation. Okay, that I'll take it to the next page. Yeah, so we express it something like this. We express it as scientific notation. Scientific notation means we express it as powers of 10. So instead of writing something like 12,435, we will express it as 1, 2, 3, 4. We will express this thing as 1.2435 into 10 raised to 4. We are expressing it in powers of 10. This is known as scientific notation. So in scientific notation, if we can easily see the number of significant figures. Okay, so so when a number is expressed in scientific notation, the exponent does not affect the number of significant figures. Okay, so this power of 10 is not important. Don't count this. This is not included in the significant figure. Okay, always ignore it. Rest, whatever the number may be, count the number of significant figures. So here is 3, here also 3. Here this 0 is not important, so this 3. Here these two zeros are not important, so 3 again, and you guys get the idea. Okay. Now, to avoid the ambiguity in situations like this, 101 with 2 zeros, we should not write it this way. The way which we should follow, let's say we want to express 101.00, okay, and this was measured with an instrument with 5 significant figures. Okay, so we want to show 5 significant figures. Then how we should write it is, so what will be the power of 10 here? 1, 2, 3, 4, 4, right? So 101 with 2 zeros, this you can write it as firstly 1.0100, okay, 1.0100 into 10 raised to 4. This is how it should be written, because looking at this, it is clear that, okay, here we can see it is 5 significant figures. Okay, here we can see it is 5 significant figures. Now, if you want to show 4 significant figures, okay, if significant figures was 4, then you will represent 101 with these 2 zeros as 1.010, okay, we'll only include 1 0 here, into 10 raised to 4. Okay, so this gets rid of the confusion. So these 2 zeros at the end, it creates confusion, and to avoid that confusion, we use scientific notation. Okay, so we'll do some questions now. 0.165. So this has how many? This 0 before the non-zero ones are not significant. The other 3 are significant. So 3 is the answer here. Here 2 zeros are sandwiched between non-zero. So everything is significant. 1, 2, 3, 4, 5. Right? What about this? Here we have 3. These 3 are the significant ones. 201. 201 will have 3. Okay. And here 5 and 0, these are going to be significant. So 2 is the answer. This is not significant. Okay. Scientific notation, ignore the 10 raised to 4. So we have 4 different significant figures here. So the answer here will also be 4. What about this? Ignore the 10 raised to 23. 3 digits. So these 3 are significant. If you have a 0 between 2 non-zero numbers, that is significant, right? And here we have 0.000. So these 4 are not significant. And these 4 are significant. Okay, so here also the answer will be 4. Okay, so for significant figures, you can just follow the simple rules. Okay. Occasionally questions are asked from this topic. So now there are some rules when it comes to adding and subtracting that should be kept in mind. This concept is also tested in NEET. So rule is simple. If you are adding or subtracting two numbers, okay, then the result, whatever you get, you have to round it off. Okay, you have to round it off such that it becomes the same number of decimal places as the term having least number of decimal places. So what this rule is saying is, this is term 1, first number, and this is the second number. This guy has 3 decimal places. This guy has 1 decimal places. So if you just subtract them and get the mathematical result, it will be 0.087. Okay. But if you notice, this has 3 decimal places. That you have to round off and bring it to 1 decimal place. Which term has the least amount of decimal places? This guy, and it has 1 decimal place. So you have to round this number such that the result also has 1 decimal place. So 8, 7, right? So get rid of this 7 and make it, we will see how to round off numbers after a while. But this is kind of easy. So we'll do it here. So after 1, getting rid of the last digit, you can write it as 0.09. We need to get 1 more decimal place away, so it will become 0.1. Okay. So you will approximately, this will be approximated as 0.1 due to this rule. Okay. So that is it. Then for division and multiplication, the rule is slightly different. Okay. If you multiply these two quantities, here the rule follows least number of significant figures. Okay. So here the number of significant figures counted 2. Here the number of significant figures counted 3, which is lesser 2. So final answer should be rounded off to 2 significant figures. Okay. So if you just multiply it, you will get the answer as 8.76. So if you round this off, it will be 8.8. Okay. So that is the rule when it comes to multiplying. Same with division. Okay. So there was a NEET question in which they asked density calculation, and they gave the mass and volume of a cylindrical wire. Okay. They gave the radius of the wire, length of the wire. They also gave the mass of the wire. Okay. So the thing is, how will you calculate it? You will substitute mass, you will substitute volume, and you will get an answer, right? But you will also have to pay attention to the significant digits. Here you are dividing, right? Here you are dividing. So let's say this has x significant digits. mass, okay, and let's say volume has y significant digits. So the final answer should be rounded off, okay. Final answer should be rounded off. And how many digits should it be rounded off to? That depends on x and y. Whichever is lesser, that much digits should be there in the final answer, okay. So that's the rule for multiplication. And so now there are some simple rounding off rules which we have to take a look. So for rounding off, it is not very complicated. We start from the last digit, okay, and if this digit is bigger than 5, which means either 6, 7, 8 or 9, then the guy before this, the guy just to the left of it, 8, you increase it by 1 and get rid of that 7. So it will become 6.9, okay. So if this digit is greater than 5, which means 6, 7, 8, 9, then the preceding digit, which is 8, you increase by 1. That's it, okay. So if it is 3.88, you get rid of this 8 at the end and increase this 8 by 1. So 3.9, okay. So that is the rule when the last digit is bigger than 5. Okay, this is only applicable when the last digit is bigger than 5. Then we have the next case where the last digit is less than 5. So this can be 1, 2, 3, 0 also, 0, 1, 2, 3, right, or 4. Less than 5. If the last digit is any one of these, then you don't touch the guy to the left and simply remove it. So this will be 3.9. If you want 3.83 rounded off, you get rid of this 3 and keep the 8 untouched. So this will be 3.8. Okay. So that's the rule when the number is less than 5. So for the number, if it is equal to 5, then there is a weird rule. Okay. And the rule is, if the preceding digit, which means the digit before the last digit, if that is odd, then we increase it by 1. If the preceding digit is even, then you leave it unchanged. Okay. So whenever you have 5 at the end, check the digit just before it. If it is odd, 3 is odd, so you increase it by 1. So it will become 14.4. Now, in another example, if it is even, if the preceding digit is even, then you don't change it. Okay. So the number before 5, if it is odd, increase it by 1. And if it is even, then you leave it untouched. Okay. That is the rule that NCERT follows. So we also need to follow that. Okay. You guys, any doubts? Any doubts so far? Okay, so now there are a few more rounding off questions and you have to round it off to 4 significant figures. Okay. All right. So now let's start. How many significant digits are here? Here we have 5 digits, right? So what is the last digit? Over here, the last digit is 9. So we increase this 7 by 1. So this will be 36.88. What about this? Now we have 4 significant figures. Over here the last digit is 4, so we keep 8 untouched. So this will become 1.008, and over here, okay, over here we have 5, so we have to use the rule for 5, right? So for 5 the rule was, if the digit on the left is odd, then we increase it by 1. So this will become 11.12. And the last rule is, here we have the left digit to be even, so we keep it as such. Number is 5, so the preceding digit, it is even, so we keep it untouched. That is the rule. Okay. All right. Great. Okay, so that is it. That is rounding off. Okay, so now we will start with errors. Okay. So for errors, so for firstly, what is error? So error is basically, so whichever measurement we make, okay, we will have to use some instrument to make that measurement, right? And any instrument you use, it will have some uncertainty, okay? Like what we mean is, if you're trying to, let's say, measure the weight of an object and you're taking multiple readings, okay? You're taking, let's say, 3 or 4 readings. In the first reading, you got the answer as 12.2 grams. The next one, you got it as 12.3 grams, 12.4 in another one, and 12.1 gram. Okay. So the thing is, let's say the true value, actual weight of the object, the true weight was 12.3 grams. Okay. So the thing is, in the first measurement, there is an error of 0.1, right? 0.1 grams. In the next measurement, there is no error. In the third one also there is error, and in the fourth one also there is error, right? So error is basically, there is always some uncertainty that occur in the measurements, okay? Always in measuring values, there is a possibility of having an error. There is no instrument that is error free, right? So error simply, it's the difference between the actual value of any physical quantity, true value, like here the true weight was 12.3 grams, right, of a physical quantity, and its measured value. So whatever is the difference that you get, that is the error, right? So here we have an error of 0.1. Always consider the positive value itself. Here we have an error of 0.1. In the second measurement, there is 0 error. In the third measurement, just subtract these two, there is an error of 0.1 gram. And in the fourth measurement, there is an error of 0.2 grams, right? So another thing is, how do we get the true value, right? How did we get the true value? Like we just mentioned that the true value is 12.3, right? But how do we get that? So the answer is, there is no way to clearly find out the true value. It's just that we have to take multiple readings, okay? Let's say we took n readings of the weight. Take n readings and take its average. And finally, we take the average. Finally, we take the average. Okay, and this average we consider as the true value. So like an example for that is, let's say we are measuring the diameter of a spherical ball. Okay, we are measuring the diameter of a spherical ball. So in the first reading, it came out as 1.22 mm. In the second reading, it came out as 1.24 mm. In the third reading, it came out as 1.21 mm. And let's say we are taking n such readings, okay, whatever that number n may be, we are taking n such readings. So if the actual diameter is d, then we take the average of all the readings. How do we take the average? We add them all up, a1 plus a2 plus a3 plus however many readings you took, divided by the number of readings. Okay. This average value of n readings, we just consider it as the true value. Okay. We just consider this as the true value. Because the thought process is that if we take too many readings, then after sometimes the effect of the error becomes negligible, right? If we take too many readings, then the effect of the error will be gone. And we can approximately get a decently true value of the diameter. Okay. So that is the idea of the true value. So if the since the true value is generally unknown, the true error cannot usually be determined directly. This is not true error. This is true. This is also true value itself. True value we cannot simply determine. We have to take the average of multiple measurements and just consider that as the best estimate. Okay, we just consider that average as the best estimate of the true value. All right. Now there are some definitions. So these are more useful for boards, and sometimes you can be asked this in NEET also. So first thing is absolute error. So absolute error is basically the difference between the true value and the measured value. So let's say true value is 80 and I'm taking it as 12 centimeter or 12.15 centimeter. And let's say first reading was 12.12 centimeter. So in this case, the absolute error, we will denote it using delta A. Okay, delta A means absolute error. And we'll also use a 1 in the subscript. 1 stands for absolute error in the first reading. This will be equal to the true value 12.15 and you subtract the reading value 12.12 and the answer is 0.03. The answer is 0.03 centimeter. That will be the error. Okay, and usually we only consider the magnitude, so we also take the mod. Okay, so even if the inside thing becomes negative, we just consider their mod value, the magnitude. Okay, so that is the idea of the absolute error. It's the difference of the true value and the measured value. Okay, so now the next thing is, so this we already covered. If the true value is unknown, we don't know about the true value, then we take the average of all the measured values. Okay, and this basically is another way to write that. So the true value, you can write it as A1 plus A2 plus A3 plus, add all the terms and divide it with n. This is your true value. This is what we will consider as the true value. Okay, and that using mathematics you can write it like this: sigma notation. Sigma ai from I equal to 1 to n. That means A1 plus A2 plus A3. You add up all these terms. Okay. Then we have mean. Mean means average, absolute error. Okay, so this means average of absolute errors. So we learnt what is an absolute error. So mean absolute error means of the absolute error, we want an average. We want an average value. So for this, what we do is we add up the absolute errors: delta A1, delta A2, delta A3. however many readings there were in the experiment and divide it with the number of readings. Okay, and remember all of this should be positive. Okay, all these values must be positive. Absolute error we always substitute as positive only. We only consider the positive error. So that is how we calculate the mean absolute error. Mean means average, right? So average absolute error. Okay. So we can also take a question. So relative error, this is the next one. This is the ratio of the absolute error to the true value. Okay. Absolute error to the true value. So once you get the average value of the absolute error, okay, so here they have written it with an M sign. M means mean, so I'm going to also write it like that. So find this value and divide it with the true value, which was also written as AM. This is the relative error. Okay, this is the relative error. This is the relative error. Okay, so relative error, in one line you can write it as absolute error divided by the true value, delta A by A. Okay, delta A by A, that is the relative error. So these definitions you have to keep in mind, guys. Then finally you have the percentage error, which is basically this relative error. You express it as in a percentage, so you simply multiply this with 100. Okay, so if the relative error after some calculation this came out as 0.003, then percentage error, you just have to multiply this with 100, so that will be 0.3 percentage. It will be 0.3%. Okay, so now, yeah, so this example we will try to deal with all of it. So there are how many observations here? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 observations, right? Yes. So first thing is, what is the most accurate length of the cylinder? So all of this is a length of a cylinder that was measured using a vernier caliper. First question is, what is the most accurate length of the cylinder? Which is, in short, they're asking the mean, the true value. So the process is, we have to find the average of all these lengths, right? So you have to add up all these lengths and divide it with the number of observations, which is 8. So I'll just use a calculator. Please see loss of motion in the next class. Loss of motion, actually this is for, so we have a batch for which is Arjuna NEET, and so these classes are basically all the topics we have covered in that batch. Okay, so in that batch we haven't started loss of motion yet. 0.3, 0.29. So let's see what we get as the answer. 3.31, 3.28, 3.27, 3.29, 3.30. Okay, so if I'm not wrong, the true value is coming out to be 3.28875. Okay, you add up basically all these values and divide it with 8. So now you have to keep something in mind. How many significant digits are here? 1, 2, 3, 4, 5, 6. Okay, whereas the measurements only have 3 significant figures, right? And this is obvious because it was measured using vernier caliper. So we have to round this off to 3 significant figures. So what will this be? I guess if you make it 3 significant figures, it will be 3.29, right? It will be 3.29 centimeter. You have to round this off, okay? So this, you have to convert it into 3 decimal places. This 875 you need to get rid of. Finally, you'll get 3.29, right? So 3.29 we will use as the true value of the length. Okay. Now, what is the absolute error in each observation? Okay. So in the first observation, the absolute error is, true value is 3.29. This is also 3.29, so answer is 0. In the second measurement, the absolute error is 0.01. Okay, just consider the positive values. In the third value, the absolute error is 0 once again. And in the fourth value, the absolute error is, it will be minus 0, so 0.02, right? So, but we only consider the positive value, 0.02 centimeter. And in the fifth measurement, the absolute error, this is the fifth one, is 0.01 centimeter. And in the sixth measurement, the absolute error will be 0.02, right? 0.02. The seventh, 0, it will be 0 centimeter. And finally, in the eighth measurement, the absolute error is 0.01. So we found out the absolute error in each measurement. Okay. Then C option is finding the mean absolute error. So absolute error, you have to find the mean value of this. So how do you do that? Mean of anything is you add everything up and divide it with the number of observations. So you basically add all these 0.01 plus 0.02 plus 0.01 plus 0.02 plus 0.01, and there were 8 observations, so divide it with 8. So the answer is coming out to be 0.00875. Okay, this is what we are getting as the mean absolute error. Okay, so you can also round it off. So here there are 2 decimal places, right? So here also you can make it into 2 decimal places. So I guess this will become a 9, 0.9, you can make it into a 0.01. Okay, but let's just keep it like this. Okay, let's just keep it this way. This is the mean absolute error. Then we have relative error. So relative error, all you have to do is this mean absolute error, just divide it with the true value. Just divide it with the true value. Okay, so I wrote the true value as L true. So just divide it with the true value. You will get the relative error. Percentage error is basically this multiplied with 100. So there is nothing to do extra there. Okay. So that is it. Then the thing is, finally express the result in terms of express the result. So the result is the length of the cylinder, right? Length of the cylinder. So how do we represent it? We will represent it as the true value plus minus the error. This is how we will represent the length of the cylinder. Okay. Delta A mean is 0.00875. That we will write it here. And here we will write the true value, which is 3.29. Okay. This also you can round it off to 2 decimal places if you want. So any quantity, any measurement which has error, you can write it like some true value plus or minus its error. Okay, this is the mean, okay, or basically what we consider as a true value. Let's say true value, and this is the error or uncertainty. Error or uncertainty. So what this means is, let's say the length measurement came out to be 12.56 plus or minus 0.01 centimeter. Let's say this was the length measurement. So this means the measured value on average, after taking all the average values, the most confident value is 12.56. We are confident that it is 12.56, but there can be an error of 0.01. So which means the length will lie between, subtract these two, it will be 12.55, right? Then add these two, so you get 12.57. So the length value, we are 100% confident it will be between these two values. Okay, that is what this means. Expressing the length like this means length will be between this thing minus 0.01 and this thing plus 0.01. Okay. So in this case, the actual value will lie between AM minus delta A to AM plus delta A. Okay. So here we will write the absolute mean error. Here we will write the true value that we got after taking the average. Okay. Okay, so now least count. Least count, we already covered. It's the smallest measurement an instrument can make, right? So if you're talking about an ordinary ruler, it can measure, the smallest length it can measure is 0.1 centimeter. So this is called the least count of the ruler. And for the vernier caliper, the smallest length it can measure is 0.01 centimeter. So this will be the least count. And for the screw gauge, it can measure the smallest length up to 0.01 centimeter. So this will be the least count. Okay. This will be the least count. So least count is basically for any instrument, what is the smallest value it can measure? That is the least count. Okay. Now there is a small fact here. Okay, this is to be noted. If the least count of an instrument is not specified, okay, not that way. I'll mention it in a question. Okay, I'll mention it in a question. So now this topic is also very important. Propagation of errors. Okay, so if you add two quantities or subtract two quantities, what happens to the final quantity? So let's say we have some quantity C which we obtain by adding two quantities A and B. Okay, and A, we can write it as the whatever the measured value is plus minus the error, okay, which we don't know, plus minus the error. B, we can write it as the measured value plus, sorry, this will be BM, some measured value plus minus the possible error which is delta B. Okay, the possible error which is delta B. Now, even if you add or subtract, the absolute error gets added. Okay, in the final result, the absolute error will get added. So let's say we are doing A plus B. Okay, then C you will write it as, so you have to add A and B. So this measured value you will add AM and BM. This value you will add. Okay, and for the error part, you will add the absolute error, delta A plus delta B. Okay, you will add the absolute error. Now, if we have another quantity C, which is A minus B. So here, how will you write it? Here, the thing is, the main value you will subtract AM minus BM. AM minus BM. But the error part is still added up. Okay, delta A plus delta B. So absolute errors, even if you're subtracting two quantities A and B or adding two quantities A and B, the absolute error always gets added up. Okay, so here also the absolute error is added, and here also it is added. Okay, so that is the rule for addition or subtraction. Okay, just add the main values, measured values, or subtract the measured values depending upon if you're adding or subtracting, but the absolute errors always add them. Okay, then multiplication or division. Okay, this is a bit more complicated. So here also the logic is the same. Let's say we have some A which is AM plus or minus delta A, B which is BM plus or minus delta B, and we are trying to divide them, okay, or multiply them. So let's say we have another quantity A into B. So we are trying to find another quantity which we get by multiplying A and B. Okay, and this quantity Z, we can write it as Z M plus or minus delta Z. Okay. Now this main measured value is easy. If you are multiplying two quantities, simply multiply the main values, AM into BM. So this main value is easy, AM BM. But this error part is slightly different. So for this, you need to write down their fractional errors. Okay. So if you multiply two quantities, what is a fractional error in Z? Fractional error is absolute error divided by measured value, delta Z by Z. This will be equal to fractional error in A, which is delta A by A, plus delta B by B. Okay, so here you can replace it with the AM value as well. Okay, so now we know everything. Delta A we know, AM, delta B, BM, ZM. All of it we know. Using this relation, you can get the absolute error in Z. You can find absolute error in Z, and then you can substitute it here. Okay, so to take an example, let's say A is some length which is given to be 12.5 centimeter plus or minus 0.1 centimeter, and B is given to be 2.08 or 10.2, let's say, plus or minus 0.01 centimeter. So there is another quantity Z, which you can write it as, which is basically A into B. We are trying to multiply A and B to get another quantity Z. We have to find the true value of Z and the error. Okay, Z, we have to find the true value and its error. Okay, so true value is easy. You simply multiply the main values, the true values of A and B. So if you multiply 12.5 with 10.2, it's 127.5. Okay, so this main value or true value of Z is 127.5 and centimeter. So this will be centimeter square. Now for the error, you will have to use the fraction rule, right? Fractional error rule. Delta Z by the main Z value, which is, I'm going to write it here, equals delta A by A plus delta B by B. So now delta Z divided by 127.5, this is the main value of Z. What is the error in A? 0.1 divided by the main value is 12.5, measured value. Error in B is 0.01 divided by the true value here is 10.2. So from here you can find delta Z. So let's try to do it. 0.1 divided by 12.5 plus 0.01 divided by 10.2. This thing multiplied with 127.5. So 1.145 is what I'm getting. So the error in Z here is 1.145. Okay, 1.145. Once you get this, express the answer as the true value of Z plus or minus the error in Z, which is 1.145. And if you multiply these two, the final unit will be centimeter square. The logic for finding the error is the same even if you're dividing, okay? Or even if you are dividing, the logic for finding the error is the same, okay? Division or multiplication, this is how you find the error using this relation, okay? This is how you find the error even if you are dividing or multiplying, okay? Now, okay, so now the thing is, if you have another quantity which is a raised to some power, okay, then here also the fractional error of x, delta x by x, this power will come up front, n times delta a by a, fractional error of a. So this is actually directly proven from the previous fact. So x equals a raised to n, right? So you can write it as a into a into a into and so on until n times, right? So fractional error in x will be fractional error in a plus fractional error of a plus fractional error of a, and this happens for n times, right? So if we add the same thing n times, so it will become n times delta a by a. So if you have x which is n a raised to n, then fractional error of x is equal to n times fractional error of a, okay? So this means if you have x is equal to, let's say, a square, and this a was given to be let's say 2 plus or minus 0.001 centimeter, okay, 2.2 let's say, then a, so x how will you find it? First do a square, okay, take the true value of a which is 2.2, so find 2.2 square, that will be 4.84, right? So write it over here and then write the error. For the error, you will use that relation, fractional error relation. Delta x by x is equal to 2 delta a by a. So we need delta x, right? We need to solve for delta x. So it will be 2 into delta a is 0.001. True value is 2.2 of a. You have to multiply with x also. X came out to be 4.84. Okay, and this will be your delta x. So 2 times 0.001 times 4.84 divided by 2.2. So this is 0.0044. This is the error in x. So finally, what will be the answer? 4.84 plus or minus 0.0044. This will be the answer. Okay, and a square, which means unit is centimeter square. Okay, so if you have a square, here you will have a 2. If it is a cube, there you will have a 3. Okay, so that is how you find the error when you have some a square type of a relation. Okay, now basically we are combining a raised to p, b raised to q, and c raised to r. In the previous we only had a. Now there are 3 different quantities. Okay, so here also the pattern is the same. If you want fractional error in x, delta x by x, what is the power of p? That comes, what is the power of a? It is p. So p will come up front, multiplied with the fractional error of a, and power of b is q. So q will come here, multiplied with the fractional error of b, and power of c is r. So r will come here, multiplied with fractional error of c. Okay, so that is how we write the percentage error when we have a raised to p multiplied with b raised to q multiplied with c raised to r. Okay, and this type of question is very important. So I'd like to take an example for this. So if x is, let's say, a square, b cube, c raised to 4, then how will you write the fractional error? Fractional error will be, or relative error will be, 2 delta a by a. Power of a comes front into relative error in a. Power of b is 3, so 3 you will write here, multiply with relative error of b, and 4 will come here, multiplied with relative error of c. Okay. Now in some question they will give you percentage error of a, b, and c. Okay, they will give that this is equal to 1%, 2%, and 3%, let's say. And then they will ask you what is the percentage error in x. So this delta x by x is called the relative error, right? This is the relative error. Percentage error is nothing but this thing into 100, right? This thing into 100. So all you have to do is multiply all these terms with 100, then you get the percentage error. So if you do that, delta x by x into 100, this is the percentage error in x. So there is a 2 here. What is delta a by a into 100? Percentage error in a, which is 1%. So this will be 1%. Then here we have a 3. What is the percentage error in b? 2%. And over here we have a 4. And percentage error in c is actually 3%. Okay, so overall the percentage error in x is 2 plus 6, 8, 8 plus 12, 20. Overall the error is 20% for x. Okay, So I hope this is clear. When you have a square, b cube, c4, the powers, put them in front of the relative error. Okay. This is true even if they are fractions, like this can also be a raised to half, then also this is the case. Okay. Then also this is how you do it. Now there is a slight modification. We put one term in the denominator, but there is no difference. Okay. While calculating the percentage error or the relative error, there is no difference. P will come here into relative error of A. Q will come here into relative error of B. Now here the thing is, if the power of C is R, then R itself will come here. Okay. It's not minus R that will come. It is R itself into relative error of C. Okay. So even if you're dividing with C raised to R or multiplying with C raised to R, it's the same. Okay. It's the same. So now we can take this question. Initial temperature of water is given to be 40.6 plus minus 0.2. So this is the measured value and this is the possible error, right? Final temperature is 78.3, that is the measured value, plus minus 0.3, which is the error. Calculate the rise in temperature along with proper error limits. Rise in temperature means increase in temperature, which is delta T. So you will have to subtract, right? You will have to subtract. So let me see the chat. Okay, guys, you can ask any doubt if you have it. Okay, I'll answer it. 78.6, 78.3, right? That is the final temperature and initial was 40.6. So if you subtract it, the answer is 37.7. 37.7, but plus minus the error. Plus minus the error. We have to calculate the error, right? So here we are just subtracting, right? So absolute error gets added up. So 0.2 and 0.3, you simply add it. So this will be 0.5. This will be 0.5 degrees Celsius. Okay. Because we are subtracting the two temperatures, the absolute error will get added up. All right. Then we have this question. Here cube side length is given. It is 2 centimeter and possible error of 0.01 in the measurement. Calculate the volume and surface area of the cube. So volume formula for the cube is side length cubed, right? So, so volume we will express it as the true value plus or minus the error, right? So for true value it is easy. Just look at the side length of the cube. It is 2 centimeter and cube it. So that will be 8. This will be 8. Now we need the error in volume. Now here we have that exponent form. So use the fractional or relative error formula. Delta V by V equals 3 into delta A by A, right? So error in volume divided by true value of volume, which was 8, equals 3 into delta A is 0.01 divided by 2. Okay, this is what we are getting. Then so this comes out to be 0.12 if you solve it. Okay, so this error in volume comes out to be 0.12, and units you can write it. It is of course centimeter cube. So now if you write it here, the answer is 8 plus or minus 0.12 centimeter cube. Okay. So you have to always write the true value plus or minus the error, possible error. Now how do you do the surface area? Surface area of a cube, you have to use that formula. It is 6a square. There are 6 square faces of a square area. So it will be 6a square. So surface area also you will express it like this. Okay, take this as homework. You will find the true value by doing 6a square, and you have to find the error. But the error you have to pay attention to this thing. This 6 has nothing to do with the error. Okay, delta s by s will be equal to the power 2 will come forward into delta a by a. Okay, so while writing the error, the fractional error relation, this 6 will not come here. Okay, this coefficient of a square will have nothing to do with this equation. This power will come in front of delta a by a. Okay, then solve this and get the answer for delta s. So this you can do as homework. And yeah, so this is one of the questions. Okay, this is one of the questions that is very important. So here the idea is simple. Some x quantity is given and 4 other quantities are also given, and they are raised to some random powers. Okay, you have to find the percentage error. So firstly, write that percentage error formula. So it will be, so a's power is 3, so this will be 3 into percentage error of a plus power of b is 2, so this will be 2 into percentage error of b. What is the power of c? C is inside a square root, right? So power of c is half. So that half you will write here, half into percentage error of c, and d's power is also half, so half multiplied with percentage error of d. So write down the error relation. Now percentage error of a is given to be 1%, so this will be 3 into 1, which is 3%. Percentage error of b is 3, so 2 into 3 will become 6%. Percentage error of c is 4%, so that into half is 2%. And percentage error of d is 2%, so that into half is 1%. So this will be 12, I guess, right? 10, 12, yes. So 12% is the answer. Okay, so now this question you guys take as homework. Okay, this you guys try it out as homework. Here I'll explain the logic. Distance measurement is given, time measurement is given. You have to calculate the speed of the object. Okay, speed is equal to distance by time. Okay, this is just constant speed motion. So speed you can write it as distance divided by time, and do what we did so far. Okay, and then you will finally have to express speed as true value plus or minus error in the speed. Okay, so try this out as homework, guys. So that was it, guys. Any doubts here? Any doubts here? Okay, guys, then okay, so then we can end the lecture, guys. Okay, we are done. Good night, take care. Okay. All right.